All right. So welcome to Naming Ionic Compounds lecture. On the day that you have class, you will have an um, ionic compound quiz. Well, I mean the polyatomic ion, sorry. You'll have to take a quiz on the polyatomic ions. So by now you should be at least like somewhat familiar with them. But let's go ahead and start. So let's kind of recap on what an ion is. So an ion is created when an atom's number of protons does not equal the number of electrons that it has, simply because this creates a charge in the atom. If you recall from the previous lectures that the number of protons minus the number of electrons is the charge of a specific atom. You can infer an element's charge based off of its position on the periodic table relative to the nearest noble gas. And I'll show you what that looks like in a moment. Ionic compounds are electrically neutral, meaning that the negative and positive charges in the ionic compounds themselves will cancel each other out and equal zero. And this is the case for all ionic compounds that have no charge. So they should have a net charge of zero. So the cations, the positively charged portions of these compounds, should be able to cancel out the anion's negative charge. All right, and so looking at this periodic table here, let me get my pen. You can see that there are charges, I will circle them for you guys, associated with each, I believe these are called groups here. And these are going to be the general charges of these atoms when you are looking for them in like ionic compounds or whatever they are. So generally hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium are all going to have a +1 charge. These guys are going to have a +2 charge. These guys generally are going to have +3. This row is generally going to be +4, but it depends on the situation. But generally, it's going to be a +4. We're not going to go into any like ionic compounds that are like super complicated, like you would in general chemistry, in which carbon could have like a -4 charge, but or like another charge other than just +4. And then notice that the charges become negative after you reach nitrogen. So these guys will generally have a -3, a -2, and a -1. And then always keep in mind that the noble gases, they don't react with anything, and they're going to always have a charge of 0 because they are okay with that. Xenon's a weirdo, but you will learn more about that in general chemistry as opposed to this class. But yeah, so let's go ahead and keep going. So like I said earlier, you can identify the charges within ionic compounds themselves. So you must be able to use ratios of elements in the ionic compounds using this formula here. And if you did everything correctly, the charges of A, so like this guy right here, should be able to cancel out the charges of B, and you'd get a net charge of 0. So just as an example, magnesium chloride. So we have 1 magnesium, and the charge of magnesium is +2, right? And then we're going to do the chlorines now. So we have 2 chlorines, as indicated by the subscript right here. That indicates that there are 2 chlorine atoms that are present in this compound. So we're going to put a 2 for Y, and then the charge is -1 for chlorine. Doing the math, 2 plus -2 gives you 0. And that's how you know that it's an ionic compound, because it's the net charges should ultimately cancel out to 0. And you could do this again with like these other compounds as well. Okay, so before we go into naming, we need to know the difference between type 1 and type 2 metals. So type 1 metals are going to be metals in which their charge do not change ever. So this includes groups 1 and 2. So this group here highlighted. I'll show you a bigger picture in a moment. And then it also includes aluminum, zinc, cadmium, and silver. You're just going to have to memorize these specific type 1 metals. The easiest way that I memorized them when I was taking general chemistry was I remembered there's a staircase going down here like this, usually used to indicate like the line between the metalloids and the non-metals. You'll find that in a lot of periodic tables. But basically, if you draw a staircase this way, and then you draw another staircase going the opposite direction, so going to the left like this, the ones underneath the first 3 steps, so right here, here, and here, are all of the type 1 metals that have the distinct charge to them. And then when we're talking about type 2 metals, they're basically all other types of metals. And when we are naming compounds with type 2 metals, we always have to include a Roman numeral. Otherwise, we are not going to be able to know what the charge of that metal is because it can change depending on the way that it's bonded with the other atoms in the compound. So like, for example, you could have iron oxide, or you could also have iron oxide. In this case, iron has a +3 charge. In this case, iron has a +2 charge. So using the Roman numerals is important when we're distinguishing between metals that can have more than one charge. All right. So going off of what I said earlier, so type 1 metals are everything that's in a blue box. So that includes all of these guys here. Keep in mind, hydrogen is not a metal, so we're not including that. And then we have our reverse staircase here that I was telling you guys about. And the reason why this is so convenient is because aluminum has a +3 charge. Zinc and cadmium have a +2 charge going down like that. And then silver has a +1 charge like that. So literally, if you just remember to do this reverse staircase, it's very easy to remember the charges of them and also just where they're at, which ones are considered type 1 metals. All right, so let's go into the naming process of ionic compounds. So let's first talk about binary ionic compounds. So remember, a binary ionic compound consists of one cation element, such as sodium. Keep in mind, sodium is a cation because it has a +1 charge, so it has a positive charge. And then one anion element, such as chlorine. Chlorine is considered an anion because it contributes a negative charge. When we are naming ionic compounds, we always start by stating the first element, the cation. So like NaCl here, we start with sodium, right? So that will be the first part of our name. The second word in the anion, you change the ending to "ide." So you can see how with chlorine up here, chlorine, we simply took out the "ine" and replaced it with "ide." So that's how we got sodium chloride. Same thing here. We have sodium, we start with sodium, and then we have sulfur. Then we took out this ending and added "ide," sulfide, sodium sulfide. You use the "ide" when you are using anions. So, you know, sulfur in this case was an anion and chlorine in the other case was an anion as well. Things get a little tricky when you are dealing with type 2 metals. So type 2 metals can have many different charges, like I said earlier. So you must indicate the charge with a Roman numeral following the cation. So it should be right here. In this case, copper is the cation in both cases. So the Roman numeral has to be immediately after that. It's important to see that in these compounds right here, we know that oxygen, based off of the rules that we established earlier, has a -2 charge. Same thing with this compound here. Copper in this one, in the lower example here, only contributes a +1 charge, but the reason why it's stable is because we have 2 copper atoms attached to the oxygen. So in reality, there's 2 positive, it's a +2 net charge for copper that it contributes to the compound. So overall, the charges of copper in this compound are +2. And then of course you have oxygen, which is -2. And look at that, its net charge sums up to 0. Same case with this one, except copper contributes a +2 charge just by itself. So it doesn't need an additional copper atom to counteract that negative charge. As long as you have the charges that are canceling out, you know you're doing it correctly, and you can determine the charges of individual atoms based off of deductive reasoning like that. So like, let's say you had this compound here and you were asked to assign the charges for each. Let's say, okay, so we know iron has a charge that can change. However, we know oxygen has a pretty set charge of -2. Therefore, we can deduce this is +2. Now, this is where knowing your polyatomic ions comes important, because this part will not make sense if you don't know your polyatomic ions. So when you're naming an ionic compound with an oxyanion, which is a polyatomic ion with oxygen, and an example of that you should already know is sulfate, which has a -2 charge. You're going to use the suffix "ite" or "ate." So for example, let's say we're working with the polyatomic ion ClO3-, which is chlorate. Its ending is going to end just as 8 by itself. So let's say this was sodium chlorate, for example. So this charge doesn't exist anymore. This compound here, sodium chlorate, is how we would name it. If we take out an oxygen, this becomes sodium chloride. And then we take out another oxygen, this becomes sodium hypochlorite. So we add the prefix hypo when we are reducing the number of oxygens in that polyatomic ion. And the opposite is true when we're adding them. So we do, let's say we were doing sodium perchlorate. We add per when we have an abundance of oxygens in the polyatomic ion itself. Now this can be tricky because there's no set rule to like how many oxygens are assigned to which suffixes and prefixes. So let me show you what I mean by that. So you can see here, this is nitrate and this is nitrite. It has 3 oxygens for nitrate, but if we look over at sulfur, a sulfur polyatomic ion, this has 4 oxygens, yet they both end with 8. So that's where your note card could come in handy, just knowing these prefixes and suffixes, or just like memorizing the polyatomic ions in detail, so that you know which prefixes, which suffixes you need to use in order to name an ionic compound with these oxy ions. And of course, if you need help, be sure to ask your TA. when it comes to naming these, because it can be a bit confusing and a lot of students mess up naming because of this. When we're doing it with polyatomic ions, so not oxyanions, even though they are considered polyatomic ions. So non-oxy ions, which of course are the ones that are different from the rest, can be named with the name of the polyatomic ion itself. So you'll notice that some polyatomic ions have very unique names. One of which is cyanide, so Cn minus. You have dichromate, which is Cr2O7. And you also have hydroxide. These names of these polyatomic ions will basically just never change. So you just pop it in the name. So you put the cation first, and then you put the name of the polyatomic ion following it after. So pretty straightforward. Let us know if you have any questions, but other than that, go ahead and start on your worksheet.